To work around the same origin policy, attackers can try to inject code using an attack called cross-site scripting. Unfortunately, this attack is quite common. For example, here is a CERT advisory about Huawei modems. Notice that it says that the broadband modems include a web interface, and this web interface is vulnerable to a cross-site scripting attack. A cross-site scripting, or XSS attack, aims to subvert the same origin policy. In particular, an attacker can construct a malicious script to try to trick a user's browser into running it as if the script came from a trusted origin. Doing so gives the script access to the sensitive content and pages from that origin. A cross-site scripting attack works by fooling the victim site into sending the script to the user's browser, which will run it with the full privileges of the victim. Let's see how this can be achieved. There are two types of cross-site scripting attack. The first we'll talk about is called stored or persistent cross-site scripting. In this attack, the attacker leaves their script on the vulnerable web server, for example, bank.com. The server will later unwittingly send that script to your browser, and your browser, none the wiser, will execute it within the same origin as the bank.com server. Visualized, it looks like this. First, we have the bad website, bad.com, and we have the vulnerable website, bank.com. Step 1, bad.com injects a malicious script to the bank.com website. Second, a client connects to the bank.com site, and bank.com unwittingly sends the malicious script along with its content back to the client's browser. The client's browser will then execute that malicious script as though the bank website intended to provide it. As a result, that script can do nefarious things like perform attacker actions such as initiate a bank transfer or steal secret data like document cookies to send back to the bad.com site. So in summary, the target is a user with a JavaScript-enabled browser who visits a user-influenced content page, that is, a page whose content can be influenced by prior interactions with users, like the bad.com site. The attack goal is to run a script in the user's browser with the same access provided by the server's regular scripts, and in this way subvert the same origin policy. To do this, the attacker needs the ability to leave content on the web server, for example, using an ordinary browser. The attacker might also have a website to collect stolen information. And the key trick here is that the server will fail to ensure that content uploaded to its page does not contain embedded scripts. Let's look at an example of a cross-site scripting attack, the Sammy MySpace worm. So MySpace was a social networking site prior to the rise of Facebook that was very popular, and it allowed people to create custom web pages. Sammy embedded a JavaScript program in his MySpace page. MySpace attempted to filter these scripts, but in this case it failed. As a result, users who visited Sammy's page ran the program, which made them friends with Sammy, displayed, but most of all, Sammy is my hero on their profile, installed the program in their profile so a new user who viewed the profile got infected, and as a result, Sammy went from 73 friends to 1 million friends in 20 hours and took MySpace down for a weekend to boot. The second type of cross-site scripting attack is called reflected cross-site scripting. Here, the attacker gets you to send the bank.com server a URL that includes in it some JavaScript code. The bank.com site will echo some or all of that script back to you in its response, and your browser, none the wiser, will execute the script in the response with the same origin as bank.com. So here this is visualized. The browser will visit bad.com, the nefarious website, and it will send back a malicious page. The client will then click on a link on that malicious page, which will take it to bank.com. The link will contain some JavaScript code. Bank.com will then echo back the link in its response to the user, and the browser will then execute the script as though the server meant to provide it. Once again, the attacker can perform nefarious actions as a result. So the key here is echoed input. Reflected cross-site scripting attacks need to find instances of good web servers that will echo user input back in the HTML response. So, for example, here's an input from bad.com where to the search term it provides the term socks. When this goes to victim.com and it sends the results back, notice that socks are included in the body. Now the problem arises when that input includes scripts. So here's an example script that's included in the URL. If that script is not filtered out, it will be included in the body returned from victim.com, and the JavaScript interpreter running in the user's browser will execute that script rather than simply print it out. And of course, the script will execute within victim.com's origin. To summarize, a reflected XSS attack targets someone who is using a JavaScript-enabled browser to access a vulnerable web service. The service's vulnerability is that it echoes back part of the URLs it receives in its output responses. The attacker goal is to run the attacker's script as if it had the origin of the victim's site. The attacker does this by getting a user to click on a URL that contains JavaScript code. This code is then reflected in the server's response to the browser. And so the browser runs the script as if it were from the origin server. The key here is that the origin server reflects the attacker script unchanged. This indifferent reflection of the input points to the proper defense. Validate the input. In particular, the vulnerable server should either check or sanitize input from untrusted sources. One form of validation is sanitization. In particular, a server can remove all executable portions of untrusted, that is, user-provided, content that it could appear in HTML pages. For example, it might look for script tags and filter them out. Then, instead of running the script, the browser will end up printing it in the document. This might look a little strange, but it will be harmless. Such filtering is often done in the comment sections of blogs. Commenters are permitted to provide rich content like boldface formatting or italics or underlining, and they can express this using various HTML tags. However, they are not permitted to include tags that would demarcate JavaScript code. Blacklisting particular tags like the script tag and removing them from the input is a natural idea. The problem with it is that there are many ways to introduce JavaScript code. You may think you have them all when you actually don't. For example, it turns out that you can embed JavaScript as XML encoded files or as a cascading style sheet, that is, CSS tag. Moreover, even if you found all of the tags that are specifically indicated as allowing scripts, there may be other ways of specifying code that is browser-specific. In particular, browsers have often been known to try to be helpful and render mangled input. Such permissiveness is good for making busted websites look okay to a user, but it can be exploited by a clever attacker. For example, such permissiveness was the flaw that allowed Sammy to evade the MySpace filter. Internet Explorer permitted splitting the JavaScript tag into two words, Java and script, across two lines, even though other browsers would not interpret this as being a JavaScript tag. This split tag evaded the MySpace filters. A better validation approach is to use a whitelist. In particular, a site can allow a certain small set of tags. It can then check that the input only has those tags in it. Any other tags that appear, well, in that case, the input is rejected. The same sort of whitelist applies to all elements of a page that could be affected by untrusted sources. Returning to our blog example, a whitelist filter could check that the URLs or other user comments contain only boldface, italics, and underline tags, and no other tags. Or the blog could permit only a more limited language for providing comments. So rather than full HTML, it could allow, say, Markdown. One note. We have just considered two different attacks with strikingly similar names: cross-site scripting and cross-site request forgery. What the attacks have in common is that one site tries to act with the privileges of another site, hence the phrase cross-site. XSS works by exploiting the trust a browser has in data sent to it from a legitimate website. So the attacker tries to manipulate what the site sends to the browser. CSRF exploits the trust a website has in data sent from a semi-trusted browser. So the attacker tries to manipulate what the browser sends to the site. In short, it's all about exploiting trust. The right defense is to reduce that trust as much as possible, in particular by using input validation. This theme comes up again and again in web security, and indeed in distributed system security generally. Let's finish off this unit with one more example. One popular framework for writing web applications is called Ruby on Rails. Server-side web applications are written in the Ruby programming language, and the Rails framework makes it easy for these applications to work by the web. Parameters in web requests sent to Rails applications can be Ruby objects encoded in XML, or as a format called YAML within XML. YAML is particularly desirable because it's easy to read and Ruby has good support for it. In particular, Ruby makes it easy to encode Ruby objects into YAML and likewise decode YAML strings into Ruby objects. When those Ruby objects represent integers or strings or enumerated types, then web app behavior proceeds as we might hope. However, YAML can encode any object, which it does by embedding Ruby code. Since the default YAML decoder can be used to decode arbitrary objects, it can thus decode arbitrary Ruby code. With a little work, the decoder can be made to invoke the code of the objects it has just decoded. This means that an attacker can send a carefully crafted message to any Ruby on Rails application and get it to run code on the attacker's behalf. Whoa. Once again, the problem here is accepting input without validating it. The problem is hidden from the application developers because the bug is in the Ruby on Rails framework and not the application. A fix to validate the input might be to reject YAML altogether, or to reject YAML-encoded objects that embed code. Of course, as with XSS, holes in the filters mean that vulnerabilities will persist. To conclude, web security introduces a plethora of vulnerabilities that application writers must guard against. All of them can be boiled down to mismatches with trust. If we cannot completely trust the source of some input, then we must validate that input to make sure that it cannot cause harm. When considering means of validation, checking is preferred to sanitization, and whitelisting is preferred to blacklisting. In our next unit, we will see how input validation is just one instance of a general set of principles we should follow when designing secure applications.